Hey everybody, Mr. D back with intervals of increase and decrease using algebra. You might recall from the example above that we were linking the first derivative function when it was above 0 and when the first derivative function was below 0 or below the x-axis. You'll notice that the breaking point, the difference between the positive values and the negative values, is when the function was actually, its derivative was equal to 0. So at these critical points here, you'll notice at this point here and this point here, that's when everything changed. And those are called critical numbers. Let's see if I could wrap that up a little bit here. So those values there are when the first derivative function is equal to 0. And that generates the critical numbers. That's a new phrase for us. Critical numbers tell us where the function changes from increase to decrease or decrease to increase. So, for example, one below, where we're doing it using algebra, find critical numbers might be one, might be more than one. Set y prime equal to 0. So the first thing we have to do, because that's going to tell us when the function changes from increase to decrease and decrease to increase. So we're going to have to find the first derivative. So here we go, leveraging the power rule from prior learning. So we get 1/3 times 3x squared plus 1/2 times 2x minus 2, and the derivative of a constant is 0, so we can simplify. So therefore y prime equals x squared plus x minus 2. And remember, we wanted to set that equal to 0. So we're going to set that equal to 0. Well, a quadratic function solving, you can use factoring if possible. And what is the other tool that we have that works for every quadratic function, factorable or not factorable? And that's the quadratic formula. That's right. And that's included in your formula booklet. So in this case, you'll get x equals negative b plus or minus b squared minus 4ac over 2a. So I'm just going to get a straight line here and get another straight line here. And there's your quadratic formula. Factoring, if it's possible, is faster. But if you're not a fan of factoring, or if you recognize that it's not a factorable quadratic, then really the quadratic formula is the way to go. Let's try to factor in the, to see if we can expedite things here. So we'll see. We want two factors that make a product of negative 2 and whose sum is positive 1. So let's think about that. Two numbers that multiply to give negative 2 but add to give positive 1. So let's see here. Negative 1, positive 2. So it looks like it is factorable. So those are our factors. We get x, whoops. And we just slide in our negative 1 and our positive 2. And we get, from here, we get x equals 1. Also, x equals negative 2. So those are our critical numbers. Well, how do we know whether a function starts increasing, then decreases and increases? How do we know if it does this versus how do we know if it does this? Because this is still a turning point, right? How do we know which way it goes? Well, we're going to have to do some algebra, but fortunately, it's more like arithmetic actually. We're going to do what's called a sign diagram. So create a sign, like in other words, SIGN diagram. And what we mean by that is we'll say, okay, if this is our x-axis right here, and we put in our critical numbers, which in this case are -2, which would be over here on the left side, and +1 would be somewhere over here, we can substitute our values. Like we can pick a test point, let's say, a value to the left of -2, in other words, smaller than -2, and determine whether or not that derivative value is negative or positive. Because you may remember up here, if the derivative function, right, just to draw your attention to that, if the derivative function is above the x-axis, in other words, if y prime is greater than 0, then we have increasing function. If y prime, the derivative function, is smaller than 0, in other words, it's below the x-axis, then we have a decreasing original function. So let's look at test points. So let's pick a test point in this interval, and it doesn't matter what it is, any number below -2. Let's pick a value in this interval between -2 and 1. The easier the better. So you pick any value between -2 and 1. And then let's pick a value that's greater than 1. So we'll call them TPs. Whoops. For short, we'll call them test points. Whoops. Let's move that away from the margins. Give me some issues there. So now we have test points. So let's pick a test point of, say, like -3 here. Of x equals -3. The easier one in between -2 and 1, as you've imagined, is probably x equals 0. And let's pick a test point greater than 1. So we're trying to determine the behavior of y prime. So this is a sign diagram for y prime. And I usually write it here so we remember to use y prime and not the original function, because the original function wouldn't really tell us a heck of a lot that's really relevant. So now we're going to go ahead and in our derivative function, which was this one here, y prime. So let's use this version, the factored version. If you put -3 in there, you get y prime equals -3 minus 1 times -3 plus 2. Y prime equals -4 times -1. Y prime equals +4. So really, we just want to know whether it's positive or negative. So if y prime is +4, that means it's above the x-axis. And when a function's derivative is above the x-axis, in other words, it's positive, we have an increasing y. So let's go back here and say y prime equals +4, which is greater than 0, therefore increasing. Therefore original function let's do the same thing for x equals 0. Always use the factored form. It's so much easier. 0 of the derivative function. 0 minus 1 times 0 plus 2. Y prime equals negative 1 times 2. Y prime equals negative 2. And that's less than 0. And we notice here, if the derivative is less than 0, we have a decreasing function. So we're getting a feel for what this function is doing using calculus. It's pretty slick, actually, compared to advanced functions. Using the derivative is so much tidier. So y is decreasing. So we know in that interval it's decreasing. And then lastly, let's just check the last one. Don't want to make any assumptions because sometimes these functions could do interesting things. So we're just going to do the quick mental math here. 2 plus 2, we get y prime equals positive times positive. So it's positive 1 times positive 4 greater than 0. Therefore, y is increasing. So the question asked, give the intervals of increase and decrease. Intervals are from negative infinity to, let's make a little room here. Let's just tidy this up. Let's go over here maybe. Therefore, intervals of increase and increase goes from negative infinity all the way to negative 2, or the other region that it could be increasing is from positive 1 to positive infinite. Interval of decrease is sandwiched in between there, isn't it? From negative 2 to positive 1. So there's your conclusion. And it's based on the first derivative. Just a quick recap, that the first thing we had to do was find the critical number or critical numbers, and that's new, right? That's actually the part of today's success criteria, is recognizing that the first derivative is going to give us meaningful information regarding the original function's behavior. So we're actually spending quite a bit of time looking at the first derivative and creating a sign diagram for the first derivative based on the factored values. In other words, the roots of that particular function. So here we of that first derivative function. So those are the key values, and they appear here. Oops, let's see if we could get that thing to recognize the rectangle. There you go. And there you go. So you notice that this one here and this right there actually appear down there. You select test points in each region, one test point per region, to determine behavior of the first derivative. So if the first derivative is greater than 0, you have what's called an increasing function. The function's going up. It's climbing, we called it earlier. If the function is less than 0, that is, the first derivative function is less than 0 at the test point, then the function is sliding. So in other words, the original function is decreasing. And go on again here, increasing, and you make your conclusion. So there you have your first example of intervals of increase and decrease algebraic.